Okay, so today we will start with our next unit, which is on interferometry. First of all, let us ask what is interferometry. So interferometry is the branch of physics that deals with the study of interference effects and the measurements of the fringes which comes out of interference, and the detailed measurement of shapes and other characteristics of the fringes. So that all can be put under the umbrella of interferometry. So interferometry even can be further classified into other sub-branches. For example, if we are interested in study of interference effects in acoustical or sound waves, we may call that as acoustical interferometry. And the whole electromagnetic spectrum also has various ranges of electromagnetic radiation. Say, for example, you have radio waves, you may have gamma rays, you may have visible region. So accordingly, the interferometry can also be divided on the basis of that. So mainly what we are actually interested in this unit is optical interferometry, and optical interferometry mainly is concerned with the visible region, where we study the light waves in the mainly visible region. Although if we refer to the whole electromagnetic spectrum, we may have to deal with the other types of instruments. So in optical interferometry, we mainly deal with those glass slabs, finding refractive index of glass slab or certain materials. So that's the main part of this unit, optical interferometry. And what is an interferometer? It is an instrument that is designed to exploit the interference of light and study the fringe patterns and other characteristics of the fringes, which results from the optical path difference among the different light beams. Basically, in an interferometer, what we do is we start with the light beam and then split it into different paths, or split it and make it to travel along different paths, and those waves or those beams are then further collected back in a single region where the interference of those beams is studied. So depending upon the history of the path along which they have traveled, they will be having different path difference, and accordingly they can lead to the interference effects. So that is what is the job of an interferometer. So interferometer very systematically tries to put light in different optical paths, and then make use of that to study the interference effects. And interferometers are broadly classified into two categories based upon what basic principle of light division they employ to create interference effects. So first one are those which are based upon the division of the wavefront, and that's why they are called the wavefront division interferometers. And second one are called amplitude division interferometers, and those amplitude division interferometers divide the amplitude of the incident beam, and then further makes it travel through different paths and then collect it back in some region where the interference of those two sub beams which are originated from the original beam is studied. And wavefront division, I hope you have studied in the previous lecture. We have already discussed it. There are many experiments which employs that wavefront division method. Say Young's double slit method is the one, Lloyd's mirror, Fresnel mirror. All these arrangements can be put under the category of the interferometers, which employs wavefront division to study interference effects. So all these arrangements can also be called interferometers. A Young's double slit experiment in itself is an interferometer, right? And the interferometers which we are interested in this unit are actually those which are based upon amplitude division, and those which we mainly are interested here are the two, which is Michelson interferometer, and second one is Fabry-Perot interferometer. So for example, we have seen in our previous classes that interference effects produced because of the light which is coming from different parts of a thin film leads to of course interference effects, and those interference effects comes under the category of amplitude division method. Means there the initial beam of light is partially divided into two categories. One is reflected partially, and other is partially transmitted, and those two, when comes back to interfere in some region, or we can say superpose in some region, they leads to the formation of interference pattern. So that's the idea of amplitude division method. So now let us discuss this Michelson interferometer. First of all, I will be talking about construction of the Michelson interferometer. What all this interferometer have to produce interference pattern. So well, this is the source of the light from where we take electromagnetic radiation, or mainly the light, means in the visible region. And then we have a beam splitter here. This BS is called beam splitter. Beam splitter is just like some slab of optically denser material, such that it is coated on this front face. So there is a coating here, just like we take example of a looking glass. Then one face of that looking glass is coated to have reflection, and in traditional looking glass the reflection is 100%, I mean close to 100%. That is why we can see things very clearly in a looking glass. But here this beam splitter is not that kind of perfect reflector. It has been coated in such a way that it partially reflects the light waves and partially allows them to get transmitted. And moreover, the traditional looking glass is coated on the back side of the glass. I mean the side from where we look into the glass, that's not coated, but it is the back side which is coated. But here it is the front side which is coated. So this portion is coated, and this material is such that it has reflection from both the sides. Means if the light falls on this side, it suffers reflection, and also when light comes from this side, then also it suffers a reflection. So it is sort of both way reflecting. Conventional traditional looking glass doesn't have that way. So it reflects light only to the one direction from where we look into the glass. So its reflectance is adjusted such that is almost like 50%. Means half of it, the light which is incident on this beam splitter, will be reflected, and half of it will be transmitted. Now well, then it has two mirrors, M1 and M2, which are placed perpendicular to the beams. So this beam, suppose, is transmitted beam. This beam is reflected beam. We are naming them with the numbers. Say number 1 refers to the initial beam, 2 refers to the reflected beam coming out of initial beam, and 3 refers to the transmitted beam coming out of again this one, incident beam, and 4 reflects the two beams together taken back after reflection from mirrors. And finally this is the region where the interference of the two is studied. So 4 refers to that. And these mirror M1 and M2 are such that they are having 100% reflection. It's just like our simple looking glasses, and they reflect the light completely. Now let us discuss the working of this Michelson interferometer. How does this work? So basically what happens is, whenever light is incident from here, so one thing you should notice here is that this source S is not a point source. It actually is a extended source. It can be a point source as well, but okay, to study the kind of things with the help of extended source, we can find out much more things, and that's the beauty of this Michelson interferometer actually, that this extended source makes it very useful. How, we are going to see shortly. So this is an extended source. So whenever light comes from here, it reaches up to this point. Both, the beam has same path, optical path. They have traveled the same path. The light beam has traveled fixed path, same path from here to here. Now here the splitting happens, and that is where the difference in optical paths begin. So this second beam has to follow this path, then face some reflection, and then this third beam has to go to this path, face reflection, and then come back, and then this also after reflection comes here, it gets transmitted through this point, it also comes here, gets reflected and comes back here. So the two beams, when they approach here or exit this point, they have definitely the different optical paths. So now, depending upon what is the optical path difference between them, these two will show the interference effect. So what we actually want to discuss now is to systematically determine the optical path difference, and based upon that we shall be obtaining condition for interference, condition for maxima minima, or bright and dark fringes, and also uh, we shall be obtaining the shape and characteristics of the interference fringes. One more thing which you should have noticed is this slab. This is also actually slab made up of the same material as that of this beam splitter, but this one is not coated. This one is not uh, coated here with the reflective material. So why is this slab required? We'll be coming to this later on. Now let us first try to see one-dimensional equivalent optical diagram of this Michelson interferometer, so that we could see things in an easier manner. So getting this diagram is little tricky, but then this diagram becomes very helpful to us. What do we mean by one-dimensional is that here we have two optical axes. One is this axis, another one is this, and these two are perpendicular to each other. So this is a two-dimensional, we would say, optical diagram. So here we want to transform this diagram to a single optical axis. So let us say this one is a single optical axis. So first of all, let us say, okay, this is the axis which we have chosen here. This same axis, vertical axis. This is the same axis here. So this is the point or region where we would be observing our interference pattern. So this is sort of observation point or observation region. And now if I would like to see this source on this axis, what do you think where this source is lying on this axis? Now remember that we can't go for a two-dimensional thing, right? So where should this source be located? So we have to see where does the image of this source actually forms here. So this source, how we should see this? So this is emitting light this, so this light is getting reflected to this direction. So if we see from here, where would somebody see this source? this source will be seen somewhere here, right? So light is reflected, and that is where we see this. You take simple looking mirror, you stand in front of it here, and if somebody is watching you from here, so where should your image be formed? It should be formed at this point. So that's the same idea. So that is where we have shown the image of this source. Say, let us say this is S dash. Now this is S dash. Fine. Okay, fine. Where will be the mirror M2? So it is, of course, somewhere here only, M2 on some point here on the same axis. And what about this mirror, M1? So we should see its image again, M1 dash. So where should it lie? So okay, this is reflecting, the light is reflected from this mirror. It comes here. So if somebody sees the image of this mirror from here, where should it be seen? It should be seen somewhere here. Same logic as we applied for the source. So this mirror should be seen somewhere here. The image of this mirror is shown on this axis as M1 dash. And suppose, so in this one-dimensional optical diagram, we have located all our components of this uh, Michelson interferometer. So we have source S dash, we have mirror 1, mirror 2, and suppose the separation between these two mirrors is, say, small d. So oh yeah, there is one more thing which I forgot to tell you, that one of the mirrors is usually fixed in Michelson interferometer. Say suppose this one, and other is provided with some arrangement by which it can move in a direction perpendicular to the beam. So suppose this mirror M2 can move in this direction, say vertical direction, or in a direction perpendicular to this beam. So basically by changing the position of this mirror, what we can play with is this small d, the distance between these two mirrors. So it is like, okay, if we move this further, d will increase. If we move this close, d will be decreasing. Now let us try to find out the optical path difference, actually, which the two beams uh, suffer. I mean, what is the let us try to find out the optical path difference between the two beams which they see because of their different paths. And for that, let us focus on this diagram. So basically, okay, this is our initial beam, beam 1. If I have to show, okay, what is beam 1? So this one is the beam 1. Fine. And what is beam 2 out of it? So this part, this total, I mean, this would be the beam 2. It will be going this way to mirror M2. It's not fully this one. I mean, we could say this full from here to here, not from here to here. Okay, this here we are actually interested in optical path difference. So this is highlighting only the path difference. This one is telling you this one. So this is the point actually where these two are being seen with respect to this. This is our reference point. So with respect to this point, we are seeing things. So what is the so because this and this path are differing only by d. So this path means path between 3 and path of 2 are differing only by 2. So this one is the reflected beam coming from M1 dash. So we can say, okay, sort of 3. This is sort of 3 coming from reflected reflection from mirror M1. This one is 2, rather this one coming by reflection from M2. Fine. So the path difference between them is d. So now we want to calculate the path difference. What do you think is the path difference? This path difference is going to be, so if you see from this point, say this line, let us see this M1 dash, the distance, this one is common for both, this one is, and this one. This is also common for both, right? Beam say 2 and 3. So the difference is only coming from this portion. The difference is only coming from this portion. I hope you are able to get this. So now we want to find out this path difference. So let us show this portion of this diagram, a little zoomed one. So this is your M2, this is your M1 dash. Now the light, this portion is showing actually the extra path which this light has to travel. So if d is the difference, distance between the mirrors, then this will be the ray which will be coming, or which will have to travel extra path all the way up to M2, and then it will also get reflected from M2. So this is another portion of that additional path which this beam has to travel, so second beam. Now we have to evaluate this total path. For that, let us draw a perpendicular here. Now since our source is extended source, so that is why the path, there is an angle theta at which the light should be seen. So if you see it from here, so it's a light comes from S to this way, say this way to this point. I hope you follow the cursor movements in my lecture. This is very important. So light comes from here and then to this point. Well, so now this is making some angle theta. So that's what we are showing here. So this is making some angle theta with respect to this axis, right? So this, if this angle is theta, what do you think? If I draw a perpendicular here, what will be this angle? This angle will also be theta. So that's what we have shown here. This angle is theta. So if actually our what we would say, the source is a point source, theta is always going to be 0, isn't it? If source is point source, theta will be equal to 0. But in that case, we will miss so many useful features of this Michelson interferometer. So that's why we don't want that to happen. So that is why we fix source to be an extended source. The next thing is observation point. See, if we are observing the interference pattern here, then again angle is of course theta. You can see this angle is theta, then this angle is also theta from laws of reflection, correct? Now if I am observing the interference pattern close to this optical axis, theta has to be very, very small. Ideally here on single, I'm in this axis, if I'm measuring observing the pattern at a very small region, in a very small region, theta is close to 0. So that is another thing which decides value of theta. So that's what we are going to see shortly. So let us first obtain the path difference. So the path difference is going to be 2d cos theta. How? That's quite simple. Let's first find out this portion, and this portion is we can obtain this from this right angle triangle. So if I write down cos of theta, that will be base upon hypotenuse, right? And what is base is d, right? So base is d. So this is this portion is so this portion is d cos theta. This portion is also same. This is also d cos theta. So total path difference is 2d cos theta. I hope it is clear to you. Now that's your I would say the optical path difference. And we have seen in interference in our previous unit or previous classes that the intensity should be equal to, then resultant intensity should be equal to 4I0 cos square delta by 2, where delta is the phase difference between the two. And now if we have to find out delta corresponding to this path difference, or say suppose any path difference, say delta in general, then this phase difference should be k times the path difference, where k is the wave vector. This can be followed quite simple. You can do a little homework in your notebook, that okay, for a path difference of lambda, the phase difference should be 2 pi, right? So what will be the phase difference for 1 unit path difference? That would be 2 pi by lambda, correct? So the phase difference for, say, delta path difference should be 2 pi by lambda into delta. So that's what we have done here. Now what will be the this total path difference or effective path difference? This effective path difference will be the sum of this path difference, which is coming because of the different paths the two light beams have traveled, and the reflective uh, component of the path difference. Means whenever the light wave suffers reflection, it may get an additional phase change of pi, depending upon on which interface the reflection is happening. So if the light is traveling from rarer medium to denser medium, and then a component of it is reflected back in the rarer medium, there will be a phase change of pi, and hence the path difference of lambda by 2. And if it is traveling, say, from denser to rarer, in that case it will also suffer the reflection. In that case, the reflected beam won't be suffering the phase change by pi. We have already discussed it. So in that case we will take this delta r to be 0. Now let us see how many reflections our beams suffer. So to see this, let us go back to the previous slide. Yeah. So here is our initial beam, right? So this, at this point, this is traveling, suppose, in the air. So at this point, this is optically denser. So beam splitter is optically denser medium, usually made up of some glass or other material. So here this suffers a reflection, and this reflection is followed by a phase change of pi, and hence one time it comes here. So let us forget C for time being. So this goes to the mirror M2. This is also optically denser, so it suffers a reflection here as well. So again there will be a phase change. So this is what we can call the external reflection. So this beam 2 actually has suffered two reflections, right? Two external reflections, means phase will change by pi first time, and second time as well it will change by pi. So total phase change will be pi here for second beam when it comes back here. So here it suffers transmission. There may be some reflection which is not useful, or we are not concerned about that. So when it will come here, the transmitted beam doesn't face any phase change. So here you would say, okay, if it is coming back, it faces this entry point, but then this point is not, I mean, whenever transmitted beam doesn't face any phase change. Anyway, let us focus on beam third. So this one, from here it gets transmitted, so no phase change. It comes here to mirror M1. So this is optically denser, phase change by, say, pi. It comes back here, it reflects. So what do you think? Here it is going from denser medium, right? It is traveling in denser medium. This is the interface of denser and rarer medium. So again getting reflected back to the denser one. So there is no phase change here. So effectively the second beam suffers two phase changes due to reflection, and third beam suffers only one phase change due to reflection. And this is what makes this factor here pi, or lambda by 2. Phase difference we have to take lambda by 2 here, because one beam has suffered an additional path change because of deflection. So that's the point here. So now let us obtain the condition for dark fringes. So what will be the condition for dark fringes? This total path difference delta, we would say, which is equal to this, just this delta p. The path difference is just 2d cos theta, and this is lambda by 2 coming from reflective part. So for dark fringes, this whole thing should be equal to m plus half lambda, right? I mean, it has to be half integral multiple of the wavelength. And if we rearrange this equation things here, we will be finding the condition for destructive interference or dark fringes to be 2d cos theta is equal to m lambda. Now let's try to visualize things practically. So suppose this is our observation plane where we want to observe the interference effects, and of course somewhere here on the observation plane we will be having image of our source. So a light which is coming at an angle theta, that will be a dark fringe if that satisfies this equation. Now if we see this cone, then for this conical area what we will be seeing for this particular value of angle theta is satisfied along this full circle here on our observation plane. So what we should see, our dark fringes or even bright fringes, you can equally well do analysis for bright fringes. So what we will be seeing on our observation plane, we should have a dark circular fringes and then dark circular fringes which will be dark and bright. Fine. So that is this circular nature of the fringes is coming from this equation. Is theta you take any line here, even if this one will also be theta. You take a line from here, this is a three-dimensional figure, join it here, then also it will be having theta. So that's what is telling us the shape of the fringes. Of course these are, say, our mirror m1 dash and m1. So d is the separation between the two, so d also has to be placed has to be in such a way that this condition is satisfied for dark fringes. So this is dark fringe. So for mirrors to be at a specific value of d, inter-mirror separation, this condition, we will be having a dark circular fringe. Then there will be a bright circular fringe, there will be dark circular fringe. Why? Okay, now this will be of different radii. So the pattern we will be seeing is for different values of m. So we can have the different values of m, and accordingly we can find out the fringes. Okay, now let us first ask what will be the maximum value of m. So if here are our fringes, then first thing which we can ask is, okay, what will be at the center, as is our usual analysis. So means on that optical axis the center point will be referring to the central fringe. Will it be dark or bright? Now depending upon this thing, it can be dark or bright as well. Means what is the separation here? So okay, what will be m max? So central means theta is 0. So means if we are observing at this point, we are referring to the central fringe, whether it is maxima or minima. So this, depending upon what is the value of t, can be dark or bright. Of course, along with this, basically theta equal to 0 is referring to the central fringe. That's the main message here. So this means whenever theta is 0, we will be having from this equation. So suppose lambda is fixed, d is fixed, then what does the value of m correspond to? So in that case, cos of theta is 1, so that would refer to the highest value of m, this integer. So means central fringe would refer to the highest order, right? This is order of the fringe, so interference fringe, so this would be the highest one. But if we go back to our conventional analysis of, say, for example, even Young's double slit method, we used to say, okay, the central fringe refers to an index which is say beginning with 0 and then 1, 2, 3, 4. But here the case is opposite. The central one has maximum value of this m, and then if you go outer away and away from the center, this m will be decreasing. How? Because theta will be increasing as we are going away and away from the center, so accordingly m will be decreasing, isn't it? This is m max, not m. So m is because cos of theta this is highest value. So if theta will increase, this will decrease. Fine. Now to go back to that customary representation of central fringe being corresponding to an integer which is 0, we try to introduce a new integer rather than going for m. We decided to, let us suppose we decide to go for another integer which is p, and we define it like this: p is equal to m max minus m. So m max is this value and m is the one following from this equation. So if I put this, we can say this is 2d upon lambda minus m, and if I put the value of m which is we can follow from here, this is 2d by lambda into cos theta. So if I substitute, I can find out p into lambda. So I can take this 2d by lambda, lambda will be coming here also to this left hand side. So p lambda will be 2d into 1 minus cos of theta. Now the values of p will be such that it will be 0 for central fringe, and it will be 1 for the next to the central, and 2, and so on. So that way we can be consistent with our previous description of interference fringes, or for example say Newton rings we had earlier done. So this is how our fringes will look like. So here, if we refer to the center point, means this point here on the optical axis, this point is exactly on the optical axis. Fine, theta equals 0. So this would refer to, say, m equals m max. So this is just an example that, okay, we have some specific value of d and specific wavelength, so that our m max comes out to be 100, suppose. Now what will be p corresponding to this? It will be 0. You can substitute the values and get this will be 0. Theta is equal to 0. Now if I go a little outward along the radius of these circles, then I will find out some other value of theta according to this equation, where m will be, say, 99. So this m has integral values, right? So m is 100, maximum value, theta equal to 0. If I go say for m equal to 99, I will end up at some different value of theta, where we will be having another dark fringe, and corresponding to that p will be 1. And when we go further to, say, m equals 98, we can find out p is equal to 2, and so on. So that's how we can characterize those interference fringes or circles with the help of another integer called p, with the central one being p equal to 0. Now let us fix one region which corresponds to a particular value of theta. Now what we are saying, okay, let us fix theta. Let's say we fix theta at this one. Now we have fixed theta. Fine. This is where we want to observe the things. And now means theta is fixed in this equation. Now let us change the value of d. What do you think this will do? If we fix theta and change d, what will that do? That will do something interesting. If we are changing d systematically, what will happen? So you will be finding that if we say increase d, now theta is fixed, lambda is fixed, correct? You are supposed taking a light of a specific wavelength. You are doing experiment with a monochromatic beam, so you will be having the bright and dark fringes of that specific color. So now we are changing d systematically. So what will happen? What theta is already fixed. So in this equation, theta is fixed, lambda is fixed. Now we are changing d. So what will have to change to adjust this change in d? This is m, which has to change. Or another way of saying this is, okay, let us say this one is corresponding to m equals 100. Then this next dark fringe corresponds to m equals 99, right? Now what about the things in between? So means when we go from this point to this point, m changes from 100 to 99. So in between, m can take non-integral values. Now you will say, okay, here you are saying m is having integer, but that is the case when we are having the dark fringe. We are referring to the dark fringe. But when we move from a dark fringe to a bright fringe, this order actually changes, say as a real number. Fine. I hope you are getting this. When we move from a dark fringe to a bright fringe and then further to next dark fringe, the order changes by one value. I mean, it's an integer, so here it is 100, here it is 99. So while moving from here to here, this has to change as a real parameter, right? So nothing to confuse. I mean, this has to be integer. No, I mean, this has to be integer whenever we are referring to a specific condition of either being on a dark fringe or being on a bright fringe. But whenever we are switching from one fringe to another, m can change as a real number. That's the thing which we want to notice here. Now, okay, so means what we are doing is we are fixing our observation point at say specific value of theta. So theta is fixed. Now we are changing d systematically. So what should happen? Those dark fringes should move, isn't it? I mean, okay, if we change d, what will happen? Those dark fringes will move inward or outwards. Why that should happen? Because this condition, initially suppose here was a dark fringe on this point, means that particular value of theta was satisfying the condition for the destructive interference. Now I changed d slightly. What should happen? That condition for destructive interference shall be satisfied if I say, okay, m has to be integer. I have to follow a specific dark fringe only, right? So in that case, I have to stick to the m being integer. So what will happen? Means the location of the dark fringe has to change on this axis. So initially, suppose it was here, the dark fringe was here, I changed d, so it has to shift to a different value of theta. Fine. So that's what we are doing actually. Means by changing d, what will happen? Those dark fringes or the bright fringes will appear to be going towards center, depending upon whether we are decreasing or increasing d. So if we are increasing d, what should happen? So if I take this equation, I take say theta, then cos of theta is inversely proportional to d. So if I am increasing d, what should happen? Theta should decrease. So if we are increasing d, the fringes should go towards the center. They should be merging into the center, correct? And if I am decreasing d, they should be going outward. They should be appearing to be originating from the center. So that's the idea here. Now, so if I am observing at this particular value of theta, so what I should observe is whenever I am systematically changing d, I would be finding, okay, fringes are crossing. Say this fringe, earlier it was here, dark fringe, it will cross this point. Then if I further keep on changing, maybe this fringe comes here and crosses this point. So that is what is the idea. And there is another important thing which we should notice is that if we keep on increasing d or changing d in a specific direction only, suppose this mirror, by changing d, what we are doing is we are moving a mirror. So if we are moving this mirror in a specific direction, so what will happen? Initially, suppose this mirror was somewhere here, so I am changing d, so means I am decreasing d. So what will happen? This mirror will ultimately reach to a distance which is equal to say the distance of mirror, say m1. If I'm still changing the direction or this I'm moving this mirror in the same direction m2, then what I should see, this will further go to this direction. So what will happen? That initially the d was decreasing. So d was decreasing means theta should be increasing. Theta should be increasing means you should observe as if the fringes are originating from this point and going outward. But the moment it crosses this point, what will happen? They will reverse their direction. So what will they do? Now if this mirror M2 goes beyond this point, what you should observe is that now the fringes, because D now is increasing rather than decreasing, so the fringes will start moving. So earlier it was so D was decreasing, means theta was increasing, so it was radiate, the fringes were moving outward. So from when the mirror crosses this point, they will be they will start to go inward. So that is what can also be seen in this Michelson interferometer experiment. I hope I could make it clear to you that how does these fringes behave whenever we try to play with D. This is something very important. Um, so okay, this is what is the thing. I mean, suppose we are observing here at a particular angle theta. So by changing this d, we can count the fringes, how many fringes cross for a particular value of d. We will see this in the applications of this. So this means if I fix d, there's another way of looking at it. If I fix D, and if suppose our mirrors are placed at a specific separation, we are not playing with this. In that case, delta theta is proportional to delta m. Means if we are going along this axis, means I'm not changing the position of the mirror. So if I'm changing delta theta, say if I'm here, suppose I change theta by this small value. This is something like, okay, I'm here on this circle, I come from here to here, so changing theta by small amount delta theta. So that is directly proportional to change in this order of interference. Means delta theta is proportional to delta m. That's what we are writing with the help of this equation. So this sine theta comes because of derivative. So I just have done nothing here but differentiated this equation. So here what we have taken d to this side, then differentiated this. This means sine theta delta theta is equal to lambda, and 2d are constant, so this is just delta m. So there is just a rearrangement. Now let us focus on this one, this equation itself, and apply a very specific condition, that suppose the separation between the mirrors is lambda by 2, d is lambda by 2. In that case, what should we have? So if we put d is lambda by 2, what we should get from here, cos of theta is equal to m. If you put the value of this here, lambda will cancel on both sides, 2 will cancel with this, so this will be m. What does this mean? This actually means that in the field of view, we will be having only one particular dark or bright fringe. So means m can only take one value, isn't it? So cos of theta is equal to m, means only one specific value of m will be there, and or what we can say is the maximum number of fringes that can be that will be present in the field of view will refer to one particular value. I mean, there will be only one dark or bright fringe in the field of view, because if you change m further, you have to change theta, right? I mean, if you change m further, um, um, what can we say from this? I mean, that's pretty clear from here, right? This, so lambda cancels, cos of theta is equal to m. So that particular value of m will be just one specific fringe for a particular value of theta, which we are saying. Uh, if the wavelength is say suppose, let us take d is equal to lambda. To see this in a more systematic manner, let us take d is equal to lambda. In that case, what we will be having, we shall be having this lambda. So this cos of theta is equal to m by 2 in that case, isn't it? This 2 will go there. So if cos of theta is equal to m by 2, then we should have two fringes, right? M is equal to 1 and n is equal to 2. Yes, what is the meaning of this is that cos theta can have a maximum value of 1, right? Cos theta can have a maximum value of 1, correct? So this means m is an integer for a constructive or for destructive interference. M has to be 1, 2, 3, 4, and so on. So according to this equation, what does it mean? M can only be 1. If okay, we are saying d is lambda, then m can be 1 and 2, because 2 by 2, that will, so there will be two dark fringes seen in the field of view. That's what is the idea here. Fine, I hope it is clear. There's another thing which we can see, that suppose we fix uh, say, yeah, now suppose we vary delta m. So basically delta m for small value of theta, so suppose theta is close to 0, then delta m will be equal to 2 delta d divided by lambda. This is the same equation we can use. Theta is suppose close to 0, then this will be 1, so m is equal to 2d by lambda. So suppose wavelength is fixed, then delta m is equal to 2 delta d by lambda, correct? Means if we are observing at center or on the optical axis, then change in order should be proportional to change in the distance between the mirrors. To see physical interpretation of this, let us discuss this example given in this book. Suppose that we are taking a monochromatic light in Michelson interferometer, and the movable mirror is translated by say 0.73 mm, and this movement, so that the mirror is provided with some screw kind of arrangement, just you see in the screw gauge, and then we can measure how much the mirror has been moved. So, and then with the shifting of the mirror, we can count how many fringes have actually merged or moved in that particular point, or we can count actually how many fringes have merged to the center, because we are close to theta is equal to 0 for this much movement. So suppose there is a shift of 300 fringes in that case. The question is, what is wavelength of light? So this is also part of what we can call application of Michelson interferometer. So if we have to measure the wavelength of light, what we do is we take the source of light, eliminate our interferometer with that source of light, and then we move the mirrors, or relative separation between the mirrors, count the number of fringes that goes to the origin for that given movement, and then based upon that we can find out the wavelength. How? Let us first try to look at that, then we will see at the second portion of this question. So lambda is equal to 2 delta d upon lambda, sorry, to 2 delta d upon m. So from this equation we can find out lambda is equal to 2 into delta d over m. We have delta d here, change in separation is here, and delta m is here, 300 fringes actually shifts or moves. So by using this equation we can find out what should be the wavelength of the radiation. That's how we can find out wavelength of the radiation from this Michelson interferometer. There is another thing, we can also find out the refractive index of a medium or a glass plate. So refer to that C plate which I had asked you to ignore. Let me go back again. Yeah, so refer to this. So this is now used here. Suppose we want to measure the refractive index of this material of that plate. So what we do is we introduce that plate into one of the arms of the interferometer. Now what will that do? So what will be, so the question is, how will this displacement of the fringe system take place when we introduce the flake of the glass, whose this index of refraction is this. Another way of doing this is, suppose we don't know index of refraction and we know how the fringe system has been shifted. I mean, we can measure how many fringes has actually been uh, shifted with glass plate and without glass plate. That is another way of finding refractive index. So, okay, how the fringe pattern will shift? In this case, when we introduce the glass plate, we know what is the refractive index for the glass plate. So total additional change in path difference will come delta D, which is equal to N G into T, the thickness of that plate, and N air into T. So N air is 1. So thickness we can measure of for that glass plate. So delta D will be Ng. So this will be just 2. So just put to find out delta M. This will be 2 into delta D divided by lambda, and this is 2, and Ng. So if we want to find out delta M, so we can put the value of Ng and then accordingly find out this value. So delta M shift of fringes will be 10.5. So means which were the shift of fringes which was earlier 300, by introducing the glass plate it will be 10.5 fringes. That's what is the meaning of this particular portion of this example. Now let us discuss some applications of this Michelson interferometer. One of the very basic application of Michelson interferometer is determination of refractive index of a gas. So of course, one we discussed in the previous example is how we can determine the wavelength of the radiation. So that's one application, how we can determine wavelength of the radiation. Now we will be discussing another one, which is determination of say refractive index of a gas. So basically we know that air has a refractive index which is very close to that of vacuum. Similarly, different gases may have different response to the light, and accordingly they may have different refractive index. So how this Michelson interferometer can be used to obtain the refractive index of a gas is by introducing evacuable cell with a plane parallel window, which is then kept in path of one of the beam. Let us see this arrangement like this. This is your Michelson interferometer. Now suppose in this path 3 we introduce a window which contains the gas of whose interfractive index we want to measure, and this arrangement is such that we can fill in this cell with the gas and also evacuate it during the experiment. So basically what we do is we do two measurements. One is without any gas filled in this cell, and then we measure the interference fringes, and then we fill the cell with the gas of which we want to determine the refractive index, and then we again measure the interference fringes. Suppose L is the length of this evacuable cell, then the path difference which comes because of the gas filling in the cell will be the additional. This is actually the additional path difference which the beam traveling along say, path 3 shall be getting. So this delta D is equal to N being the refractive index of the gas which we want to determine. So N we have to determine, we don't know, into L, the length, minus L. So this is the path which the beam has to travel anyway, even without the gas. So the additional path difference will be delta D, which is equal to this one. Now what we do is just simplify this, and for simplification what we have done is we have actually substituted this delta D in terms of the wavelength, the equation which we have used for delta D is this one. I hope you are aware of this equation. Oh, where is it? Sorry. So the equation which we have used for delta D is this. Yeah, this one. So from here we can say, okay, delta D is equal to lambda into delta M divided by 2. So delta D is lambda divided by 2 into delta M, and this L has come from here. So this is therefore n minus 1 is equal to lambda by 2L into delta M. Correct? So when we are using that equation which I just mentioned, then what we mean is that we are looking for small value of the angle, means we are looking close to the central center point of the those concentric circles. Now how to determine refractive index from here? So we eliminate the this Michelson interferometer with a light of known radiation or known wavelength. Sorry, what we do is we eliminate this Michelson interferometer with a radiation of known wavelength, and we know the dimensions of this cube. Sorry, this evacuable cell. This capital L. Sorry, this is not okay. I mean, this is not required. Fine. Yeah. So we know the length. Then we first measure the fringes in say without gas filled in the cell, and then second time we measure the fringes with gas filled in the cell, and then total change in the fringes is measured, and that is what can be then used to obtain refractive index. So that is how we can obtain the refractive index. It's a very simple idea. Next application is another very interesting, where we actually can measure the wavelength difference between two closely spaced components of spectral lines of a source. For example, you have in sodium source D1 and D2 lines which are very closely spaced, and the difference is almost like I think 6 angstroms, which is very, very small. So how we can measure the difference in two closely spaced spectral components? That can also be done with the help of this Michelson interferometer. So for that, let us again start with this expression for destructive interference, and that is for a dark fringe. Then what happens is that as long as we are observing things at a particular value of theta, or rather let us say as long as we are observing things near to the center or central fringe, in that case we can say this is equal to 1. And rather if we are not actually playing with the D, we are not changing say the separation between the mirrors, in that case this right hand side left hand side is going to be constant because we are not changing D. In that case, if we have two wavelengths, one is lambda, another one is lambda dash, then m lambda should be equal to m dash lambda dash, because the left hand side is totally constant. Now next thing which we have to do is that okay, what will happen when we have two wavelengths? In that case, what happens is that the fringes of one wavelength will be formed at a different angle, and fringes of other wavelength in general will be formed at a different angle, right? Why? Because wavelength is different, so of course there will be different angles, the different values for theta at which the constructive or destructive interference should happen, and that is how they should be observed at different angles. But now if we move D slightly, what should happen? The locations of those fringes should be altered as per D, and then the movement of those fringes will be unequal because they have a different wavelength, so accordingly they are following a different equation, so the movement will be unequal. So what happens is that there will be certain values of d where the bright fringes of both or corresponding to both the wavelengths will superpose over each other, and that is why we will be seeing very sharp intensity uh, at those maximas, and almost perfectly dark fringes at the minimum. And then when we move d further, what may happen is that okay, the maxima of or maxima corresponding to one wavelength may lie exactly in the midway between the minima for the other wavelength. I mean, midway between the maximas of the other wavelength means what we can say is the maxima of say lambda, maximas of lambda will lie on the minimas of the lambda dash, something like this. So in that case, what we can say is that the interference pattern sort of gets washed out, because we won't be able to find out those perfectly dark fringes, because there always is maxima, and since the two wavelengths are very closely spaced, so it is really hard to even differentiate between their color as such. So the interference fringes for some values of d sort of gets washed away. Now what we actually do is, okay, whenever the two fringe systems are actually coinciding, so what is the situation there? In that case, m is equal to m dash plus n. Why is it so? Because see, say, so first case, so suppose that is the value, say d1, for which this is satisfied. So the equation would be like, okay, so 2 d1 cos of theta. So now since the two fringe systems are coinciding, so theta is same for both. So let us say this term is constant, so that is equal to m dash, say lambda dash, and second one will be giving you m into lambda on the right hand side. So basically m is an integer, m dash is also going to be an integer, because these refers to the condition for constructive or destructive interference. In current case, condition for destructive interference. So m and m dash both are integers. So in that sense, what we can say is the difference of any two integers is also going to be an integer. So what we are saying is, okay, m is equal to m dash plus n, where n is another integer. Fine. Therefore, what we can say, let us suppose we are seeing things at even here in say close to say theta equal to 0 degree. So then what we will be finding, m is equal to 2 d1 over lambda. d1 is same now, I mean for both, because d1 is the distance at which both the fringe systems coincide with each other. Then 2 d1 over lambda is equal to 2 d1 over lambda dash, that plus n. So we just have substituted the values of m and m dash in same equation by taking theta to be equal to 0, means we are talking close to a central case. Fine. Now what we do is we change d further, and then fringes will move, and then what will happen, there will be another next coincidence, there will be a next coincidence as well. So what will happen in that case? In that case, m is equal to m dash plus n plus 1. So when next coincidence happens, one of the so what may happen is that okay, one of the fringe systems, say one particular fringe, say inner fringe, say goes to in inner wall, and outer one comes and overlaps with the second fringe system, something like this. So that is why this integer increases merely by 1. Well, in that case, if we substitute the values of these m and m dash now, and suppose that distance where next coincidence happens, this is d2. Therefore, what we can say is that 2d2 over lambda is equal to 2d2 over lambda dash plus n plus 1. Right? Now, if we simplify those two equations, I hope you can see here these two equations, and if we simplify these two equations, rearrange, we actually can subtract these two equations, say let us subtract from this equation this one. You can do it as a homework in your notebook, and I give it to you as a homework. So what we should find out if we subtract, what we should find out is that there will be a term corresponding to lambda. So this would be something like 1 over lambda, say d1 minus d2. Similarly, there is going to be a term on right hand side 2 by lambda dash, say d2 minus d1, and here n cancels n, and then you will be left with 1. So ultimately what you will be finding is that lambda minus lambda dash is equal to lambda lambda dash divided by 2 into delta d, where delta d is d1 minus d2. So basically, how we can find out now the difference between the wavelength? So basically, since the two wavelengths are very closely spaced, so lambda and lambda dash, the product of these two can be taken to be almost equal to lambda square, some average value. In that case, we can say the difference between two wavelengths will be delta lambda, which is equal to lambda square over 2 delta d. And delta d is something which we can measure from our scale provided for moving the mirror, say M2. So we will from that be in a position to obtain delta d, and hence we can determine the wavelength difference. So that's another very interesting application of this Michelson interferometer, that we can find out wavelength difference for very closely spaced spectral lines. Now, all the preceding discussion of the fringes from Michelson interferometer has been in terms of virtual fringes of equal inclination. Oh, I think I forgot to mention in that previous slide. So let me go back there. Sorry. Yes. If you look at coaxial diagram, yeah. So this can be seen to be like a thin film of air, isn't it? That okay, from one portion of the film, light gets reflected. Since it is air film, so there is no bending of the light here on the interface, but that's okay. And then here, some part of it is again reflected. So this situation is similar to interference caused by a thin film having, say, width d, and these are the fringes of equal inclination, because all these fringes which are observed corresponds to a specific value of inclination, that is theta. Fine. Now that's what is the point of discussion here. Sorry. Yeah, here. So this one, the Michelson interferometer. These are the fringes, virtual fringes of equal inclination. We have assumed that mirrors M1 and M2 are precisely perpendicular to each other. Okay. Now, or what amounts to the same thing, precisely parallel in equivalent optical system, just the thing which I just showed you. Fine. But if the alignment of these mirrors is such that the air space between M1 dash and M2, which is there in this figure, means this the mirror, one of the mirrors, say M1 or M2, is not perpendicular to the beam direction. In that case, what we may observe is that the fringes actually would be something like fringes of equal thickness, right? And I hope we have discussed those, so I won't be doing that in detail. But yes, we can obtain fringes of equal thickness in case those mirrors are not what you call perpendicular to the beams, and those will be of equal inclination if they are uh, perpendicular to the beam or parallel to each other. Now that's I think all, but yes, there are certain other interesting aspects. So for example, this diagram I have taken from the same book which I'm following for this unit. This diagram is referring to the fringes which I mean has been altered because somebody has placed a candle in the path of one of the beam. So why do you think these fringes have been altered? because of a candle placed in the path of a beam? Uh, well, I won't be giving my answer right now to you. I leave it as a thought question to you people. You can even try to search it in the book. And why such kind of what you call this deviation happens in these fringes because of a candle placed in one of the path of one of the beams. So, well, with this, I think we have completed uh, this Michelson interferometer and its applications. Next thing which we will be discussing is Fabry apparent interferometer. So that I will be doing in the next class. Till then, stay safe. If you have any doubts, you can put your questions to me on discussion forum or even on the WhatsApp group. Thank you. Thank you very much.